We'll start in 1 minute. Today we'll be in section 6.4. This is more about factoring, the general strategy for factoring. So we attempt to look at the big picture, everything at once. So the first thing, if the greatest common factor is not equal to 1, then factor that greatest common factor out of all of the terms. Try to learn the special forms and how to identify them. This form, a to the second plus 2ab plus b to the second, is a perfect square trinomial. Its two factors are a plus b times a plus b. Another perfect square trinomial form is a to the second minus 2ab plus b to the second. And its two factors are a minus b times a minus b. The difference of squares, a to the second minus b to the second, one factor is a minus b and the other factor is a plus b. So the binomials are conjugates. A to the second plus b to the second. In this class, we don't learn how to factor a sum of squares. So we say not factorable. Using real numbers. A sum of cubes can be factored, a to the third plus b to the third. There's a binomial factor, a plus b. And then a trinomial, a to the second minus ab plus b to the second. A difference of cubes, a to the third minus b to the third, can be factored. The binomial factor is a minus b. And the trinomial is a to the second plus ab plus b to the second. Okay, step 3 in the general strategy for factoring. If we have a trinomial of the form ax squared plus bx plus c, we can use the AC method to see if it can be factored with integer coefficients. If you have a polynomial with 4 terms, those are called quadrinomials, then you can attempt to factor by grouping. And sometimes rearranging the terms will allow you to factor by grouping. And at other times, factoring by grouping won't work using integer coefficients. And you can always check your factoring by multiplying the factors. Okay, well, we'll look at a bunch of different cases. So we'll factor a bunch of polynomials until time runs out. So the first one, 7b to the second plus 7b minus 42. The greatest common factor is 7. So we factor 7 out. And then we have b to the second plus b minus 6. And then we check to see if we can factor b to the second plus b minus 6. So let's set that aside, b to the second plus b minus 6. We want to see if we can factor this. Let's use the AC method. So 1 times negative 6 is negative 6. The coefficient of b is 1, so we want to find two integers that have a product of negative 6 and a sum of positive 1. It doesn't take too long to find negative 2 and 3. Negative 2 times 3 is negative 6, and negative 2 plus 3 is 1. So this can be factored. So transform it into a quadrinomial, b to the second minus 2b plus 3b minus 6. And then factor by grouping. Out of the first two terms, factor out b. And the binomial is b minus 2. Bring down the middle operator of addition. And then out of the third and fourth terms, 3b minus 6, we can factor out 3. And the binomial b minus 2 stays behind. So this factors to b minus 2 times b plus 3. So our complete factorization up here is 7 times b minus 2 times b plus 3. Okay, we have a quadrinomial to the right. The greatest common factor of all 4 terms is 3. So let's factor 3 out first. And then we have 5RT minus 5R plus 4T minus 4. And then the quadrinomial inside the parentheses, we'll see if we can factor that by grouping. So inside the parentheses, out of the first two terms, 5RT minus 5R, we can factor out 5R. And we're left with T minus 1. The middle operator is addition, so we bring down the middle operator of addition. Out of the third and fourth terms, the greatest common factor is 4. So we factor 4 out, and we have T minus 1. And then our next step can be the complete factorization. We have a factor of 3 times the binomial T minus 1 times the binomial 5R plus 4. Okay, now we have k to the fourth minus 16. Well, this is definitely a difference of squares. But it's also a difference of fourth powers, because 16 is 2 to the fourth. So if you take college algebra, you'll learn more about differences of nth powers, where n is a positive integer. But here I'm just going to mention it in passing. So we'll treat this as a difference of squares because we know how to factor a difference of squares. So let's write it as k to the second squared minus 4 to the second. And we know how to factor a difference of squares. So one of the factors is k to the second minus 4, and the other one is k to the second plus 4. We can factor further because this factor here, k to the second minus 4, is also a difference of two squares. So this is k to the second minus 2 to the second. So one of its factors is k minus 2. The other factor is k plus 2. And the sum of squares, we just leave that as k to the second plus 4. So this is the complete factorization in math 1108. In college algebra, you would factor k to the second plus 4 also. But in this class, we just stop when we have a sum of squares like this. Okay, the next one, y to the sixth minus 1. Well, this is a difference of cubes, and it's also a difference of squares. Because 1 to the third is 1, and 1 to the second is 1. So let's view it as a difference of squares first. So y to the third to the second. So we have something squared minus 1 squared. And when we factor this difference of squares, we have y to the third minus 1 times y to the third plus 1. But y to the third minus 1 is a difference of cubes. We know how to factor that. The other one is y to the third plus 1, a sum of cubes, and we know how to factor that. So first we'll factor y to the third minus 1. The binomial factor is y minus 1. And then we have a trinomial, y to the second plus 1y plus 1. And then we factor the sum of cubes. Y to the third plus 1 has a binomial factor, y plus 1, and a trinomial, y to the second minus y plus 1. So that is our factorization. Okay, let's move on to the next page. So that's all we're going to do today is factor trinomial or polynomials. So here's a polynomial in two variables, but we can still factor it, or we can attempt to see if we can factor it. So let's try the AC method. We still just use the numerical coefficients. So 1 times negative 58 is negative 58. And we want to see if we can find two integers that have a product of negative 58 and a sum of positive 27. Okay, let's go through the thought process here. If two numbers have a product that is negative and a sum that is positive, well, one must be positive and one must be negative, and the one with the largest absolute value is positive. So in our systematic approach, our first pair is -1 times 58. We're picking the factor with the largest absolute value to be positive. But -1 plus 58 is positive 57. So the next pair, what's the next pair of integers in our systematic approach? So go ahead and type it in. The next pair of integers in our systematic approach. -2 and 29. That is correct. -2 and positive 29. The product is -58, and the sum is positive 27. So -2 and 29 are the two integers that we're looking for. So we transform the trinomial into a quadrinomial. We write x squared minus 2xy plus 27xy minus 58y to the second. Sorry, my middle term should be plus 29xy. -2 and 29 are the two integers. Okay, then we factor by grouping. Out of the first two terms, x squared minus 2xy, the greatest common factor is x. And when we factor x out, the binomial is x minus 2y. And then we bring down the middle operator of addition. And then out of the third and fourth terms, the greatest common factor is 29y. So we factor 29y out. And the binomial is x minus 2y. And then the final factorization is the binomial x minus 2y times the binomial x plus 29y. Okay, the next trinomial, 14c to the second minus 29c plus 12. The greatest common factor of all three terms is 1. So let's try the AC method. 14 times 12 is 168. So we want to see if we can find two integers that have a product of 168 and a sum of -29. Okay, if the two integers have a product that's positive and a sum that is negative, then both integers must be negative. So we'll use our systematic approach. We're picking pairs of negative integers that have a product of positive 168. So at the extremes, we have -1 times -168. Then -2 times -84. Those add up to -86. Negative 3 is a factor. Negative 3 times negative 56. The next pair, negative 4 times negative 42. Those add up to negative 46. We're getting closer. Negative 5 is not an integer factor, but negative 6 times negative 28. Those add up to negative 34. The next pair, negative 7 times negative 24. Those add up to negative 31. What's the next pair of integers?
Negative 8 and negative 21.
Yeah, negative 8 and negative 21. Negative 8 and negative 21. So I'll use this as an example when writing down pairs of integers that have the correct product. I'm using previous answers to help me with the later answers. So if you look at negative 4 times negative 42, well, it's easy to use this factorization, negative 2 times negative 84. If I double negative 2 to negative 4, I take half of negative 4 to get negative 42. And similarly, for negative 8, well, negative 8 is 2 times negative 4, and negative 21 is 1/2 of negative 42. See what I mean? So anyway, those are the two integers that we want because they add up to negative 29. So this guarantees that we can factor it. So we transform the trinomial into a quadrinomial, 14c to the second minus 8c minus 21c plus 12. And then we factor by grouping. Out of the first two terms, 14c to the second minus 8c, the greatest common factor is 2c. And the binomial is 7c minus 4. And a reminder, at each stage, you can check the results by multiplying. 2c times 7c is 14c to the second. And minus 2c times 4 is minus 8c. So we proceed to the next step. The middle operator is subtraction. So we always bring down the middle operator. The greatest common factor of negative 21c and 12 is negative 3. Sorry, it's 3, but this minus sign reminds us that we want to factor out the negative of the greatest common factor. Factor out negative 3. Negative 21c divided by negative 3 is positive 7c. 12 divided by negative 3 is negative 4, so we have minus 4. The two binomials match, so our complete factorization is 7c minus 4 times 2c minus 3. Okay, I'll give you a couple of minutes to work on this one. After you find the factorization, it should be pretty simple to type in if you're going to type in the factorization of 63n to the second plus 150n plus 75. So see what you can get done in a couple of minutes. Did you get it? Anybody online get the answer? Well, everyone in class got it. Okay, so the first step, oh, I got an answer online, but let's go through this. The greatest common factor is 3. So we factor 3 out, and we get 21n to the second plus 50n plus 25. And then we'll use the AC method on the trinomial. So let's work on that over here, 21n to the second plus 50n plus 25. So 21 times 25 is 525. We want to find two integers that have a product of 525 and have a sum of 50. So if the product is positive and the sum is positive, both must be positive. So in our systematic approach, we have 1 times 525. 2 is not a factor, but 3 is. 3 times 175. 4 is not a factor. 5 times 105. 6 is not a factor, but 7 is a factor. 7 times 75. 8 is not a factor. 9 is not a factor. 10 is not a factor. 11 is not a factor. 12 is not a factor. 13 is not a factor. 14 is not a factor. 15 is a factor. 15 times 35. And 15 plus 35 is 50. So we can factor this guarantees that we can factor this trinomial. Okay, so I'll include the factor 3, and then we'll transform the trinomial into a quadrinomial. 21n to the second plus 15n plus 35n plus 25. And then inside the parentheses, we'll factor by grouping. So out of the first two terms, 21n to the second plus 15n, we can factor out 3n. And we're left with the binomial 7n plus 5. Bring down the middle operator of addition. So we have plus 35n plus 25, factor out the greatest common factor, which is 5. And the binomial is 7n plus 5. And finally, the complete factorization is 3 times the binomial 7n plus 5 times the binomial 3n plus 5. Okay, the answer on YouTube is correct. Same factorization I got anyway. Okay, moving on. More practice. Factor v to the second minus 25vw plus 46w to the second. The greatest common factor of all three terms is 1. So we'll try the AC method. We just multiply the coefficients. 1 times 46 is 46. If possible, find two integers that have a product of positive 46 and a sum of negative 25. Okay, so if the product is positive and the sum is negative, then both must be negative. So in our systematic approach, negative 1 times negative 46 has a product of positive 46 and a sum of negative 47. What's the next pair of integers to test?
Negative 2 and negative 23.
Okay, negative 2 and negative 23. Negative 2 times negative 23. And those do have a sum of negative 25. So negative 2 and negative 23 are the two integers we're looking for. So that guarantees that we can factor this. So we transform the trinomial into a quadrinomial. And we can write v to the second minus 2vw minus 23vw plus 46w to the second. And then we factor by grouping. Out of the first two terms, the greatest common factor is v. And the binomial that stays behind is v minus 2w. Then the middle operator is subtraction, bring down subtraction. And above that, we group the third and fourth terms. So 23 is a factor, and so is w. So we're going to factor out negative 23w. And we're left with v minus 2w. And the complete factorization is v minus 2w times v minus 23w. Okay, move on. Let's move on to the next page. So factor 8m to the third plus 27n to the third. The greatest common factor is 1. So we're just looking at a sum of cubes. The variable parts are obviously cubes, but so are the coefficients. So if it helps, you can rewrite this as the term 2m to the third plus the term 3n to the third, and then use the sum of cubes factoring formula. The binomial is 2m plus 3n. The first term in the trinomial is what we get when we square the term 2m. Then we're going to subtract the term 2m times 3n, and then plus what we get when we square 3n. Okay, but we should simplify those products a little bit further. When we square 2m, 2m times 2m is 4m to the second. And then minus 2m times 3n is minus 6mn. And then plus, when we square the term 3n, we get 9n to the second. So this is our factorization of the sum of cubes. Okay, the next one, 1000x to the third minus 729t to the third. So what is this one? This one is a difference of cubes. 1000 is 10 to the third. 729 is 9 to the third. So we can rewrite this so that it is more obviously a difference of cubes. So if we raise the term 10x to the power 3, we get 1000x to the third, x to the third. And then we're subtracting the term 9t to the third. Then apply the difference of cubes factoring formula. We have a binomial factor of 10x minus 9t. And in the trinomial, the first term is what we get when we square 10x. The middle term is plus 10x times 9t. And the third term is plus the term 9t squared. Okay, we'll simplify a little bit further. When we square 10x, we get 100x squared. And when we add 10x times 9t, that's the same as adding 90xt. And then when we square 9t, we get 81t to the second. Okay, the next one, 25xw to the second plus 1000x. Okay, what's the first step on this one? Well, the greatest common factor is not 1. 25 is a common factor. 25 goes into both 25 and 100. And each of the terms has one factor of x. So the greatest common factor is 25x. And after we factor that out, we have w to the second plus 4. W to the second plus 4 is a sum of squares. So in this class, this is our complete factorization. In college algebra, you will learn how to factor w to the second plus 4. Okay, but for us, we move on to the next problem. The next one, 81c to the second plus 54c plus 9. The greatest common factor of all three terms is 9. So we have 9 times 9c to the second plus 6c plus 1. We saw this one yesterday, but we didn't have time to finish it. Can we factor 9c to the second plus 6c plus 1? Well, we can try the AC method. 9 times 1 is 9. Two integers that have a product of 9 and a sum of 6. 3 and 3. So we found the two integers that satisfy the two conditions. So that guarantees that it's factorable. So do you remember what we're dealing with when we apply the AC method and the two integers are the same? Do you remember what that tells us about the trinomial? Yeah, it tells us that the trinomial is a perfect square trinomial. So the two factors are identical. Okay, but anyway, if we go through the process, transform the trinomial into a quadrinomial, 9c to the second plus 3c plus 3c plus 1. Out of the first two terms, factor out 3c. And the binomial 3c plus 1 stays behind. Bring down the middle operator of addition. The greatest common factor of the 3c and 1 is 1. So when you're factoring by grouping, make sure that you don't leave out the plus 1. So when you factor 1 out of 3c plus 1, we get 1 times 3c plus 1. And then when we complete this factorization, we get 3c plus 1 times 3c plus 1. So once again, when you factor a perfect square trinomial, the two binomial factors are the same. So for this one, the complete factorization is 9 times 3c plus 1 times 3c plus 1. Okay, let's start the next page. Okay, this one, 4a to the second plus 35a plus 49. The term on the left, 4a to the second, is a perfect square. The term on the right is 49. That's also a perfect square. But this is not a perfect square trinomial. If it were a perfect square trinomial, the middle term would be plus 28a. But we can still use the AC method. So using the AC method, we multiply 4 times 49, which is 196. And we want to see if we can find two integers that have a product of 196 and a sum of 35. So if the product is positive and the sum is positive, both must be positive. So let's see if we can find a pair of integers. So start at the extremes, 1 times 196. The next pair is 2 times 98. 3 is not a factor. We already know that 4 times 49. Those add up to 53. That's not close enough. 5 is not a factor. 6 is not a factor. 7 times 28. And 7 plus 28 is 35. Okay, so that guarantees that we can factor this. Another hint that it's not a perfect square trinomial. The two integers that satisfy the two conditions are not the same, but we can still factor it. So we transform the trinomial into a quadrinomial, replace plus 35a with plus 7a plus 28a, or vice versa. And then factor by grouping. The greatest common factor out of 4a squared plus 7a is a. And the binomial is 4a plus 7. Bring down the middle operator of addition. And then out of the third and fourth terms, 28a plus 49, the greatest common factor is 7. And times the binomial 4a plus 7. And then finally, the final factorization, 4a plus 7 times a plus 7. Okay, let's try the next one. 36b to the second minus 65b plus 25. The greatest common factor is 1. So we'll resort to the AC method. So 36 times 25. Well, one thing you can do, notice 36 is 9 times 4, and 25, we leave that the same. So the reason I did that is because I know that 4 times 25 is 100, and then 9 times 100 is 900. So if you don't always want to reach for a calculator, you can learn how to break it down and do the arithmetic quicker than it takes to get a calculator. Okay, so we want to see if we can find two integers that have a product of 900 and a sum of negative 65. So both must be negative if the product is positive and the sum is negative. So we start at the extremes, -1 times -900, then -2 times -450, -3 times -300, -4 times -225. So -5 times -180, those add up to -185. -6 and -150. Okay, we're out of time, so I'll leave the rest of that for you to do. So go ahead and sign in for attendance.
So with this 63n squared, I did it wrong, I guess. Would that still come out? Because I mean, it still comes out to be all that. Oh, you didn't factor out. Yeah, I didn't factor out the.
Okay, but when you get to this stage, you can factor the greatest common factor out of that.
Oh, okay, so I can simplify it a little bit more. Yeah, I would. Yeah, okay.
Yeah, this would be 3 times and then 3n plus 5. Yeah, it still works even if you don't factor out the greatest common factor. But it's probably easier in the long run